Thank you for this nice introduction. In this session, we would like to present you the LGD Compact and also some words about the technology we use, the TDLS technology. So some words about this TDLS technology we are using. So TDLS stands for Tunable Diode Laser Spectroscopy. Tunable diode laser, we'll discuss this a bit later. The spectroscopy is a spectroscopic technique that measures absorption of radiation in function of wavelengths. If you look at the electromagnetic spectra, the whole range of the electromagnetic spectra, you will see that it's made from very short wavelengths to long wavelengths. So knowing that the wavelength is the distance between two crests, two maximum of this sine wave. And for example, the visible light is very short or a very small part of this complete spectra. And we, in TDLS or with our laser, we will work more in the higher spectra range. That is a bit, that you can see in this picture. So, concretely, to measure concentration of gas with TDLS, because it's at the end what we want to do, what we do is we take advantage of some specificity of some gases that have absorption in the higher range, so in the near IR and the mid IR, as you can see in this graph on top right of the slide. So here is just a selection of some gases because you have many gases that absorb light in this range. And if you look a bit more in detail, or you zoom inside this spectra, and we take just one gas of interest, here in this case the NH3 and the ammonia, a gas we can also measure. You see that it's made of single lines, so single absorption lines at a very defined wavelengths, in this case 1500 nanometer. And so how do we measure this absorption? The idea is to take a laser that is emitting light at this wavelength, so the one we choose to measure the ammonia, for example. And we use also here the specificity of this laser that are tunable, so you can change slightly the wavelengths of the laser, and you scan across the absorption line. So no gas, no absorption, but if you have then gas in the system, it will absorb the light and you can then measure this absorption. And with the Beer-Lambert law, you can convert this absorption in gas concentration that we normally express in ppm, for example. So this is for the theory, so how a TDLS system can look like, and Alessandra will explain how we implement that in our system.
But how do we do this in practice? We have a sample cell that will be filled with our target gas, a light source emitting in the infrared, and a detector. The detector is measuring the amount of light that is reaching its surface. If the target gas is present, it will absorb the light. Therefore, the quantity read by the detector will decrease, as we can see in this slide. The amount of how much the reading of the detector will be decreased depends on the amount of the concentration of the gas and on the path length of the light. Maybe now we can show you how it works in practice in one of our main applications. We have a video that clearly explains the theory.
When the laser beams enters the gas cell, it reflects several times between two mirrors before it hits the photodiode. The laser beam is tunable in a range of a few nanometer by varying the laser current or temperature. For this reason, depending on the spectrum, up to 3 gases can be measured with only one laser diode.
Which light sources are we using and where in the infrared spectrum are we measuring? Depending on the gas, there will be different absorption lines. The strongest will be in the mid-IR, and then we have overtones in the near IR. For our detection limit, that is our target, measuring in the second overtone is good enough. So we were using light sources in the near IR. These light sources that are emitting in the near IR are called VCSEL lasers, and is in the current wavelength range we are measuring between 1.5 and 2 microns. These lasers have the possibility to be tuned in wavelength with the current. We change the current of the laser and we can change the wavelength. In this way, we can scan the absorption band of the target gas. But how does it work in comparison to other technologies? Rui, can you please explain us?
Yes, so TDLS is one way of measuring gas, but there are also other technologies out there. So as example, we have NDIR, so non-dispersive infrared spectroscopy, where you also measure absorption, but in this case you don't have a laser, but a broadband IR source and a detector. We have FTIR, Fourier transform infrared spectroscopy, and that use an interferometer and do a scan over all the spectral range. That's also a possibility to measure gas, and also electrochemical. Different, not an optical measurement. Here is more a chemical reaction that you measure that happen between the gas of interest and the membrane, and you measure then the change in voltage of this between the cathode and the anode. This is our three example of other technology or techniques to measure gas. And if you compare to the TDLS in this graph you see, and take some point of interest, like the selectivity, like the long-term stability, like the initial cost, or acquisition cost, the cost of ownership. So do you have to change a lot of time or many times the parts, a lot of maintenance. If you can, another point is the hot gas measurement and the multi-gas measurement possibility. And if you look here, the TDLS here represented in a red curve, you see that it checks many of these interesting points, like the selectivity, the long-term stability, or the cost of ownership. The price to pay is more the multi-gas measurement that is not possible in TDLS. We can sometimes measure one or two gases, but it's not like the FTIR that can measure many of them, obviously with another price, another cost of a system. So this is really for general gas measurement. If you look now, we compare this technology to concrete applications like the CH4 measurement for leak detection. This will look a bit different, and this Alessandra will explain a bit or compare with other technologies.
So for this specific application, a measurement of methane leaks, we have different technologies on the market. We have TDLS, NDIR, MOS, IR camera, electrochemical sensor, and flame detector. What we compare is definitely different category, like selectivity, cost of ownership, price, lifetime, compactness, dynamic range, and sensitivity. Every device has an advantage, but we can see that the TDLS is the widest for this type of application. There are some prices to pay, which is a bit more pricey than other technique, and is not very compact compared to other techniques. But in general, has the best selectivity, the best cost of ownership, the lifetime, and the dynamic range and sensitivity. So, compared to other technology, this technology has the widest area for this application. But now we have enough with the theory. Rui, can you explain why we started the LGD Compact development and how did we start the journey?
Yes, so for the LGD Compact, we started development with three goals in mind. First one was to reduce the size. We have up to now the F200A ambient platform, also capable to measure methane, for example, and we wanted really to reduce the size of this system, where to address market where the portability, for example, is important, and come from this 1.9 kilo system to a system that is about 600 grams. So really a big step in the downsizing of the LGD platform. The second goal was the performance. So with a new regulation in environmental market, also tougher requirements in this field, we had to improve the performance, the lower detection limit, for example, and this is what we achieved with the LGD Compact. The third idea, or third goal, was about the cost, to popularize the TDLS technology and make it more affordable in mid or high volume market where we compete with NDIR or FID technology that are normally cheaper. We wanted to develop LGD compact or a device that brings down the price acquisition barrier for this TDLS technology. So now from the idea, the result is the LGD Compact product that you can see here in the slides. I will explain a bit some features that we get in this device. First, we have this aluminum cylinder, this extractive ambient module, and we have inside the laser, the photodiode, also the multipass cell that we show you previously in the video. We have the dimensions of this module, also big difference compared to the F200 ambient, for example, and also the weight that is around this 600 gram. A big step also on that development. We have to treat the data, we have the main board that you can also add an interface board and connect directly to the PC. The power supply, so you have to what you have to feed to the device is the power supply 10 to 30 volt if you have the interface board, or 3.7 to 5 volt if you have only the main board. Some data interface, so all TTL if it's a main board, or the RS232 if it's with the interface board, but also some analog output 420 milliamp or 0.5 volt. The low power in consumption, as it's made or thought for portable applications, we have here the consumption below 1 watt, and it could be even battery driven if needed for 8-hour use in the field. Okay, some gas fittings that will show also some different possibility in gas fittings to connect directly the gas. The gas we can measure with this platform, CH4. We have also CH4 C2H6, so in combine two gases in one device. We have CH4 CO2, we have C2H2 H2O, and coming soon the NH3 gas we'll be able to measure. Operating temperature -10 to 55 degrees corresponds to the field requirements. And the response time here, the volume of the cell is pretty small, so a T90 of 1.8 seconds at 2 liters per minute. And the sampling rate, you can have or 1 Hertz or 2 Hertz, depending on different configurations. And for the long-term stability and ensure the line locking over time, we have a built-in gas reference in the device. And this platform, so this is the main feature, so our product. We have possibility to configure this device with different cables and so on, and this Alessandra will explain what are the possibilities.
We have different possibilities to configure our LGD Compact. We have the first opportunity that we can see here is with an ESD-proof electronic box directly connected to the LGD device. Another opportunity is to get the device without the ESD safe box. We can have the main board connected and a communication board provided too. Another option is to get it without the communication board. The customer can provide himself the communication to our electronics. We could also have different type of fittings for delivering the gas to the gas cell, straight or 90 degrees. Another option we can choose from is how we want the cable to be connected, if straight or 90 degrees. Of course, it depends a lot on how the device will be integrated. But let's have a look how our options look like in real life. Here we have our electronics containing an ESD safe box. It's ready, everything is prepared with a connection cable, ready to use. Second option is main board and interface board that can be integrated in your own equipment. We can also get rid of the interface board and deliver the item just with the main board with the calibration. Regarding the gas cell fittings, here we have installed a 90-degree option, but we can sell the device even with a straight option. Another option that we have is the main cable to the board. Depending on the electronics you purchase, you will have a different connection to the board, directly to the board or to the electronic box. Then there are options 0 degrees and 90 degrees. and also different length can be provided.
We can now have a look of the devices and how they look inside, and also compare this new LGD Compact to the platform it will replace, the F200A, so the F200 Ambient. So here on the slide you see the device, the F200 on top. From inside, let's say, the idea behind was the same, so we have the laser and laser going through the measurement cell to the mirror and reflected to the photodiode. In this case, we have a dual pass for a 40 centimeter absorption length in this whole device with a 15 milliliter volume cell. The LGD Compact that we developed newly, if you look also inside, so even it's smaller in size, using the multipass cell, we could achieve double optical pass, so 80 centimeter, as you can see here, and then also increase the performance because you have more signal or more absorption of the light. With the same principle always, we have the laser going inside the cell, multiple bounds in the mirrors, on the mirrors, and reaching then a photodiode. So one USP is the multi-gas measurement. As we said before, TDLS is not really the best technology to have many gas in one device, but if you choose a spectral range with more than one absorption peak that are not so far away, then you can have this multi-gas measurement, one or two, sometimes three gases. In our case, we had two gases possible to measure in one device, is CH4, C2, H6. That is important for leak detection, for example. We have CH4 and CO2, also interesting for some medical applications. And we had C2H2 and H2O that can be measured in one device. Robustness, it's also important that when the device is in the field and with optical measurement is always very tricky. If you have some contamination or some dirt coming inside the system, you will then decrease the performance of your system. The baseline will have really high noise, and you decrease really the performance of your device. And with some clever design protected with some IP, we could really minimize this effect of the dirt that sometimes comes inside the device due to, I don't know, filters that are not well used or that are not anymore filtering correctly the gas. And you can see here, for example, we did some tests on one window, to the entry window of the cell, that we really put a lot of dirt on, and despite this highly contaminated window, so optical interface, if you look at the performance or the baseline noise, it stays within the specifications. Other USP, the size and weight for the portable application that we mentioned before, so really a small, very compact measurement, but with a higher absorption length, and calibration free, so no need for regular recalibration. And if you need some performance check, just 1 or 2 minutes enough to do some basic check on the performance of the device.
I'm introducing now our product portfolio. Our first item on the list is for sure the LGD Compact for methane. In this case, the measurement range can lay between 0 and 4% volume. The accuracy is plus minus 2% of full scale, and the lower detection limit is 0.4 ppm. Another product we are proud to introduce is a LGD Compact with dual gas, methane and C2H6, with the accuracy of plus minus 3% full scale for CH4 and plus minus 2% full scale for C2H6. The lower detection limits in this case are 0.8 ppm for CH4 and 15 ppm for C2H6. Another product we have now available is the LGD Compact for C2H2. In this case, the range is 0 to 100 ppm with an accuracy of always of 2%, plus minus 2% full scale. The lower detection limit is 0.6 ppm. The last product that is now available is a LGD Compact for CH4 and CO2. In this case, the range for the two different gases is 0 100 ppm for CH4 and 0 10% for CO2. The accuracy, plus minus 2% full scale for CH4 and plus minus 3% full scale for CO2. The lower detection limit is 0.8 ppm for CH4 and 2000 ppm for CO2. We are proud to introduce shortly also the LGD Compact for ammonia. In this case, the range we're targeting is 0.0 to 100 ppm concentration and an accuracy of plus minus 2% full scale. The lower detection limit in this case is 0.4 ppm. This is an overview of the performance of our current products. What I can show you here is an actual measurement of the performance of our device, in this particular case with the CH4. We left the device in our lab for 5 days and tried to see what happened to the measurement of the concentration with ambient air with a flow of 2 liters per minute and a sampling rate of 2 Hertz. Or we can see that the curve is not moving much, apart from this part and this part, where probably some people entered in the room. Here we see how stable it can be during the when it is undisturbed during the weekend.
So that was a small overview of the LGD Compact device. If you need further information, more detailed information, you can find that on our website, axetris.com, like the operating and integration instructions, like the data sheet, like the quick start guide, all available on the downloads section. So what is the outlook at Axetris? We are focusing on 2 main markets. One is the medical market, with the breath analysis, where we may need to go to the mid-infrared to measure ppb levels. The other one is the environmental market, where the costs need to be reduced and the extension of our gas portfolio. But for more details, you can join sessions, case study sessions later today.
So thank you for your attention, and we are looking forward to meet you again in our Q&A session.